Okay, so the final speaker of the day is Murray Elder, also from University of Technology, Sydney. And he'll answer the curious question of what is a C Cayley position-faithful linear time computable group?
Great, thanks, Mikhail. Yes, that is my goal, to answer this question on everybody's lips. So this is joint work with Dmitry and Prohrak, who are at Maydol in Bangkok, Thailand. And we made up this definition. I kind of like it. So let me show you why and then what it means, and then I'll run out of time. Pardon me. So let me begin with one of the words in the title, position-faithful. So a position-faithful one-tape Turing machine is the Turing machine which uses a semi-infinite tape, like I have a picture of here. And so it's got an end here. And the leftmost position contains a special symbol which only occurs once, and you cannot modify it during a Turing machine computation. So this is a definition of other people and hasn't finished yet. The initial configuration of the tape, you can put any inputs you like here, and then after that, you put a blank symbol forever. And so you can put any string from an alphabet that you want to use. And then we just operate the Turing machine as normal. We usually start the computation with the read head there. We move backwards and forwards as we like, but we never move off the tape here. And we never modify this special position, which marks the end point of the tape. You probably know there's many, many different definitions of Turing machines and how they operate, and often restrictions like having a one-ended tape or a bi-infinite tape doesn't make any difference to the computational power. So what else have I said here? Yeah, so these are from some alphabet sigma, and then that's the initial configuration. So that's the Turing machine model. And now what is what's the last thing? During the computation, operates as usual. Okay. So we call a function computed by a Turing machine position-faithful one-tape computable if the following is true. When you start, there it is. When you start the computation, as we said before, so maybe x1, x2, x3, x4, and then blank, blank, blank. With the read head here, the Turing machine operates as it does, rewriting, maybe rewriting very far along. And we consider the function to be computed by one of these machines if there's a Turing machine algorithm which takes input that looks like this and always outputs the prefix to be the value of the function. And then after the first dot, you don't look. It could be anything. So you could use that final piece to the right to do some sort of storage as you're going along. So that's my model. So there's no restriction. So that's how we consider the output of the tape. So you might think it's a pretty contrived, unnatural definition, but that's what we have in the literature. That's position-faithful Turing machine. So let's do some examples. I've got a function from binary strings to binary strings, and it takes the input a W and it outputs the value W+1 in binary. So is this position-faithful? And then my question in addition here, because maybe you would be able to do this if you had long enough time, but I'm asking, is it position-faithful on a one-tape Turing machine in linear time? Just added one thing. So I've got a binary number. Now, if it ends in 0, I simply just overwrite that 1 by, I start here, I scan up here, rewrite it, and this is still a blank symbol, and so that's it. And if it was a 1 there, I would move that blank symbol, and I'd write a 0, and I'd write a 1, and so on. My writing's a bit messy. So what's the answer to this question? Is this function, adding 1 to a binary number, doable on this thing in linear time? Anyone? I'll answer for you. Yes. Maybe the description is a bit hard to follow, but that's what it is. So now let me give you another function. And I'm going to ask the same question, whether this function is computable using all these restrictions that I have. So the function has got an alphabet sigma, and it takes an input. And what it's supposed to do is output the binary string v, where the input is some prefix u, and then v, and then x, and then y. So u is not allowed to include 0, 1. V is 0 and 1. And then the X is the first letter after that that's not a 0 or a 1. And I think I want V to be, well, maybe, yeah, I need to make a little thing that, you know, if there are no zeros or ones, then it'll return nothing. So I might have to make a little modification there. Okay, so it takes input, a string, and it looks at all this junk and just ignores it. And it goes to the first piece of the binary string, and it's supposed to output that. So it's a pretty simple function. It's supposed to just scan up, forget all that, and just output this. But I don't know if you remember from my slides that the rule for this model is that the output has to be sitting right next to the plus symbol. It should be f of x. And then a blank dot. And then you can have some rubbish at the end. So the challenge here with position faithful in linear time is that I have to move the pointer up, 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 and then somehow read my binary string backwards to the left. And you can prove that this is not possible to do in linear time. So it's a bit of an obscure thing. Okay, so this example comes from a paper where they define it. So there's the definition again. The function is position faithful one tape. If on input this, it outputs this, plus some junk at the end. And you have to do that in linear time. Of course, it doesn't really matter where the pointer is, because it can just scan back through the input and go back to the start. Okay, so it's a very obscure definition. I'm going to come back to the end of why we want it. And so this one is no. Okay, so two very, very machine-based functions. It's a very subtle difference. Okay, so now let me move to structures, and I'm going to get to the definition of an automatic group. So I'll go fairly fast through this. A structure is a whole bunch of things. It's a set, and then it's a whole bunch of n-ary operations, sorry, n-ary relations, and then it's a bunch of functions from a to the power of some direct product of a's into a. So that's a structure. So let me give some, let me just jump that. Give some examples of structures. So we're kind of moving in a bit into logic here. So the successor, you've got the structure, which consists of all unary numbers. And then you've got a relation less than or equal to, and you've got a function, successor. So the successor, it's a function which takes a unary number and returns unary number plus 1. And of course, less than or equal to is just less than or equal to, like that. So that would be an example of a structure, which logicians might care about. Here's a group, which maybe some people here care about or not. We've got a set A. We've got this circle relation, which is a relation. So it takes 3 elements from the set A. And it will only do that if U times V equals W in the group. So that's why I called it circle. And equals is the relation that U and V are actually equal to each other. So you can represent a group like this, and A doesn't have to be in bijection with a group. It's just a surjection onto the group. So that's the way to represent a group in this bizarre kind of notation. And one more, a label directed graph. So I've got vertices and edges, and the edges are labeled from some finite set, is my assumption. And it's directed. So we can encode this as a structure, and certainly you can do a lot more than this. So the way that I want to encode it is I tell you the list V as my domain set, and then I have a whole bunch of relations where the relation is that X and Y vertices are related if there is a directed edge from X to Y labeled by the appropriate letter. So it's just a very abstract nonsense thing to do, to take your favorite object in, maybe it's a graph, maybe it's an algebraic thing, maybe it's a logic thing, and you turn it into a structure. Okay, so a couple more bits of notation. If I have a finite set lambda and I have a symbol hash that's not in lambda, U times V here, two strings out of lambda star, you can combine them together, and this is called convolution. So U convoluted with V is either you draw U on top and you draw V on the bottom, and you put the blank symbols in the appropriate spot. So if V is longer than U, you need blanks at the top. And if U is longer than V, you need the blanks at the bottom. So it's simply a way to take two strings out of an alphabet and create a new alphabet for which these pair of strings can be read synchronously together. Okay, so it's just a convention. And if you have two languages in the same alphabet, or maybe different actually, the convolution is simply the set of all convoluted pairs. Okay, so I'm going to use that. Okay, so structures described by languages. If I have a structure and it just so happens that the first set is described to you as a set of words over an alphabet. Okay, so if you think back to my group, I just said it's a set surjecting onto the group. So maybe the alphabet could be a generating set for the group, and then the natural thing to do would be to choose words over some generating set, which is not going to be in bijection with the group. Okay, so that's where we're at. So in this situation, we can say that the structure can be described by languages. So we have the initial language, and then we have the language of convolutions of these n tuples, because this is a relation. And now these functions we can consider as mi plus 1 tuples. We consider them as the graph, basically. So we consider the whole thing as just languages. So when we have languages, we can say, well, how complicated are these languages? Okay, and so a language just over a simple alphabet here is called FA recognizable, which stands for finite automaton, if it's accepted by a non-deterministic finite automaton. So let me give you an example where every one of the languages involved in the structure is FA recognizable. FA stands for something else as well, but here it stands for finite automaton. So successor, that really simple one, the set of all strings of ones, I just drew a finite automaton with start and accept the same, accepting that. And now I need less than or equal to, so I'm going to have to accept letters that look like that. Remember the convolution? And then I need less than or equal to. So eventually I'm going to have the first guy shorter than the second guy. So I have a hash. And then after that, I'll have a hash and then a 1. So that automaton, where this is the accept and this is the start, is going to accept successor. So, less than or equal to. And successor is even easier. You would not have that and you'd have to stop here. Okay, so everybody in this structure is regular or FA recognizable. So I'm using notation from other people's papers. So finally, and this may not be the definition of automatic group that you have seen before. A structure is called automatic if A is given to you over an alphabet to begin with. A is FA recognizable, the language of these relations is FA recognizable, and the language of the functions is FA recognizable. So everybody involved is regular. Okay, so successor is an example of an automatic structure in logic. Okay, so Kruengthomya and Nerode came up with this definition of automatic for general structures in 95. And one thing they proved is the first order theory of an automatic structure is decidable. So in particular, I won't say what that means, but in particular, if you want a group to be automatic in the sense of the structure I gave at the beginning, that group had better have a decidable first order theory. And so that is going to rule out a whole bunch of groups. However, even more saddening, perhaps, is that Oliver and Thomas proved that a finitely generated group is automatic in the sense that we had above with that structure, if and only if it's virtually abelian. So it's too strong to capture a whole lot of groups, okay? So maybe it's too restrictive. So here's something that Kruengthomya and other co-authors did. The Cayley graph, when did I start? 20. Oh my goodness. The Cayley graph, many people here would know, with respect to a generating set, is you have a vertex for each group element and an edge from G to H if labeled by S, if G times S equals H. And then you continue that and you draw a big picture. So here's a group which is C2 star C3. And I've drawn the Cayley graph here. Representing group elements by these strings. And I've made a choice about how I represent the group element as a string of generators, so that there's a unique one for each one. So that's the Cayley graph. Now we already saw how to make a label directed graph into a structure. We make some choice, and I said here in bijection with G, but it actually could just be in surjection with the vertex set. So some choice of ways to label, in this case, group elements, and then a relation for each edge. And so E of SI is the set of all group elements that differ by an edge. And so now that I have a structure for the Cayley graph, I can ask, when is this Cayley graph automatic in the sense of Nerode and Kruengthomya? And so questions before we get there is, how should we label the vertices? Well, you could call each one just a group element, but if it's an infinite group, we're going to kind of run out of things. We're not going to have we're not going to be able to say automatic, because in that sense, you need some finite alphabet and a bijection or a surjection from some nice labeling onto the group. Okay. So one choice would be the generating set. That would be nice. And A would be some nice normal form to get a bijection. So that would be one choice, but we don't have to do that. So here's the definition, 2014, due to Kalimpovich, Kruengthomya, and Myasnikov, that a group is Cayley automatic, or has a Cayley automatic structure, if the set A is in bijection with the group, or it could be a surjection, over some alphabet, where the alphabet are just some weird strings, not necessarily anything to do with generators. And that the Cayley graph listed like that is an automatic structure. So in other words, everything in sight is automatic. There's a finite state automaton that can read two words at a time and tell you whether they represent group elements that differ by multiplication by a single generator. So that's what it means to be Cayley automatic. So I'll skip. So it generalizes the traditional from the 80s definition of automatic due to Thurston and many other people in one key way, that the lambda does not have to be a generating set. So let me justify that in 1 minute by this example. The Heisenberg group, which we've just seen, is a set of all matrices upper triangular with x, y, and z integer, in this case, for the discrete Heisenberg group, and matrix multiplication. So it's known that this is not automatic in the sense of Thurston et al. However, and it's generated by multiplying by these two things. There's a funny way to represent this as an automatic structure. You can write a matrix just by telling me what the numbers are. So maybe X is that, Y is that, Z is that. And then you can just write these three numbers in binary on top of each other. There's nothing to do with generators here. We're just representing group elements in our favorite way. And so now our alphabet is the alphabet of weird looking columns. Now, if I give you a big string like this, you can check whether or not it's legit with a finite state automaton. If it's got, this has to come first and then the dollars have to be in the right spots. So that's regular and in bijection with the group. And then multiplication by one of these generators is a first year linear algebra exercise. What happens to the matrix when you multiply by one of them? Well, you're just adding one to a binary number. Now that's very easy, even for a position-faithful linear time Turing machine to do. So it turns out that this is automatic in this sense of Cayley automatic, using this as a choice. So I'm going to use up my 5 minutes of questions because I apologize that I didn't. Well, we have one question to answer and I want to try and answer it. What is one of these ridiculous position-faithful things? So a result of Frank Stefan and his collaborators in Singapore is the following, that if you've got a function from an alphabet to an alphabet and you represent the function as a list of tuples, as I described before, then that list of tuples is FA recognizable by a Turing machine, by a finite state automaton, if and only if the function can be computed in linear time by a deterministic position-faithful one-tape Turing machine. That's where it came from. My original definition. It's an equivalence to having the set of tuples accepted by a finite state automaton. And to me, that was really surprising. It took me about 2 weeks in Bangkok with my collaborators to understand what the definition was. So if you didn't get it in the 20 seconds that I gave at the start. And also it's equivalent to say non-deterministic as well. So we looked at this and we thought, okay, we have this definition due to Karl and Povich et al. Of what a Cayley automatic structure is. And a lot of people have been studying this. So we thought, okay, having these structures as FA recognizable is equivalent to having a Turing machine position-faithful testing things out. So what we decided to do to generalize the notion without losing all of the great results was, inspired by this notion, we defined what a C Cayley position-faithful linear time computable group is. And here it is. You say that it has one of these structures if there's a language from a class C, where C is some formal language class like context-free or context-sensitive or something. So we're not requiring the original language to be regular. However, we're requiring, and we want a bijection between the language and the group. And the final thing that we're copying from the old definition, and because this original thing is from some weird class, like maybe recursively enumerable or something, we can't just require that the function recognizing multiplication of two of these strings be recognized by a finite state automaton. Because to begin with, it wouldn't be able to recognize if the individual strings were okay. So what we do is instead we say we require that you are able to tell whether two strings are equal multiplied by a generator that can be accepted by a position-faithful Turing machine. So that's our definition. And it turns out that many of the same results for the Cayley automatic groups are still true for this bizarre, hugely more general class of groups. So in particular, there's a quadratic time algorithm to compute normal forms, which is cool. The class includes all polycyclic groups. it's independent of generating set. And if you happen to have any C formal language class that satisfies all those things, then it has to be recursively enumerable. And our final thing, which I have no time, but it's in our paper, is that we constructed something which is a recursively enumerable but not recursive language of normal forms. However, you can compute whether two things differ by a generator. So we think that's kind of cute. So I apologize for packing so much in. Thank you, everyone, for your attention.
Thank you, Murray. Are there any questions? Well, does not seem like there are any, so
you say this class comprises the finally generated subgroups of GLNQ. Is it like exactly that class of groups?
Oh no, it's bigger. It's bigger. It includes something that's recursively enumerable, not recursive, which is probably not in here. So this is the Mihaila subgroup of F2 times F2. Actually, so it's bigger, and we actually generalize the definition even more. But yeah, we don't know how big the class is. We think lots of things are there. We're trying to prove that Thompson's group is in there, actually. Of course.
Okay, are there any other questions for Murray? Well, doesn't seem like it. So let's thank Murray one more time.